Today we are going to talk about complex addition and multiplication. When we add and subtract complex number, we add the real part and imaginary part separately. Example, if z equals a plus bi, w equals c plus di. So z plus w equals a plus c, and this is the real part, plus d plus di. So b plus d is the imaginary part. And we can also find z minus w. Example, z equals 5 plus 10i, w equals c minus 5i. So z plus w equals 5 plus 3 plus 10 minus 5i, which is a plus 5i. And the second one, w minus z, it equals 3 minus 5 plus minus 5 minus 10i, which is minus 2 minus 15i. Okay, let's talk about geometric understanding of complex addition. We can represent complex number in a graph by vector. Here is our vector z, and it represents the complex number z. And point z is 5.10. So point w is 5.3 minus 5. So what about z plus w? We move this vector w to this position. So we get the new vector, which is w plus z, and it equals a plus 5i. And w minus z is this vector, which is minus 2 minus 15i. Yeah, as you see, we connect these 2 points and get this new vector, which is w minus z. Let's think about what does the absolute value of w minus z mean. It means the distance between this point and this point. Example, if the absolute value of z minus 2i equals 1, and we need to evaluate the maximum of the absolute value of z plus 1. First, let's think about what does this sentence mean. Z minus 2i, and we find it the absolute value. What does it mean? It means the distance between point z and point 0.2. So it's actually a circle whose center is at 0.2 and ratio is 1. Here's our graph, and our point z is moving on this circle. For now, we need to find the maximum of the absolute value of z plus 1. So we move this circle right for 1 unit, and we get this new circle. W equals Z plus 1. And point W is moving on this new circle, as you can see. So when does this absolute value comes the biggest? We know in a triangle, the sum of two sides is always bigger than the other one. So A plus B is always bigger than C. A equals square root 5 and B equals 1, such that square root 5 plus 1 is always bigger than C. So when does the C comes the biggest? It's actually when this line go across the center of the circle. And this is our biggest C. So the maximum is square root 5 plus 1. And that's the maximum. Okay. Part 2. Complex multiplication. When we're doing multiplication, we can treat I as a symbol and taking I squared equals 1. Example, if Z equals A plus BI, W equals C plus DI, ZW equals this one. As you can see, I squared 2 equals minus 1. So here is minus BD. Example, if Z equals 5 plus 10i and W equals 3 minus 5i, evaluate. First, the multiple W. Is equals 15 minus n. Okay, here's the answer. And the second one, Z squared. It equals minus 75 plus 100i. Now let's think about the geometric understanding. What does Z multiple I mean? Z equals A plus BI. So here is our vector Z. If we multiply I, we get a new vector, which is minus B plus AI. It's here. And this one is 19 degrees. So we guess this vector may rotate it counterclockwise by 19 degrees. Question. If Z equals A plus BI, W equals C, and C is a real number, then what does Z multiple W mean in geometric? It means we change the length of this vector Z, but not the direction. And question 2. If z equals a plus bi, w equals c plus di, then what does z multiple w mean in geometric? To answer it, I should introduce Euler's formula. And this is the formula. I don't want to prove this formula on this video. From this formula, we know that for every complex number z, we can write it as z equals r multiple e, z equals r multiple e I theta. And you can see the graph here. So now we can try to find the geometric meaning of complex multiplication. Z is the complex number, W is the complex number, so ZW is n multiple n is this complex number. So what does it mean in geometric? As you can see, here's two property. If V is a vector in R2, V equals 1 dot 1. If V is rotated counterclockwise by 16 degrees, and its length is doubled to get the new vector W. Evaluate vector W. The vector V is here, 1 dot 1. If we want to rotate it by 16 degrees, it comes here. And its length is doubled. So our new vector is this guy. How can we calculate the position of this point? We use complex multiplication. We can write vector V as 1 plus I. And we rotate counterclockwise by 16 degrees. We can write it as, and length is doubled. Now we calculate this sentence. It equals I write it here. As you can see, this point is 1 minus square root 3 square root 3 plus 1. And that's our vector W. Okay, thank you for watching. Here is my reference.